So vulnerability analysis and resilience strategies, that's what we're going to dig into here. Um, good. So just to start with a little bit of a framework, thinking about resilience planning, you can think about it in terms of this diagram is one way to do that: causes, effects, and then ultimately planning. So starting from the left is climate science, and Morgan talked a little bit about that. So it's thinking about the future, having predictions. There's a lot under the hood there, and we'll talk a little bit about that. But it is starting from that point, and then exposure. Exposure is the degree to which an asset, and so it's physical things, but also operations, processes, could face climate hazards or be exposed to those climate hazards. And then, so that is essentially, the cause. That's the forcing function, climate and exposure. And then the impact, and the impact has two dimensions. So the impact really is the potential for a negative outcome once exposed. And the two dimensions there are sensitivity, and sensitivity really is the likelihood that that asset isn't going to perform as designed when exposed. And consequence is just that. It is what happens when that asset fails to perform as designed. And consequence could be considered with respect to the system or with respect to customers, and effectively, it's most effective to do both, right? So a robust analysis considers how the failure of an asset affects this system and ultimately how it affects customers. And we'll talk more about that. So the combination of exposure and impact is what we term vulnerability. And so just the overall potential to be affected. And from there, there's this risk assessment dimension where you are determining the risk to asset groups. So it's like, what is the risk to transmission lines or our transmission system? And then even more detailed as you drill down, and I'll talk a little bit about that. What's the risk to specific assets? And then after that, you grapple with the question, well, what are we going to do about that? What are the investments that we're going to make to address these risks? Climate science provides the foundation for the analysis. There are two or three points here that I really would like you to take away is one is no one knows the future, right? It's dependent on a number of different things. So there is uncertainty. That uncertainty is captured in scenarios. And so you see the spread here on the slide on the right. There are these SSPs, shared socioeconomic pathways. Essentially, there are a set of scenarios that describe a range of outcomes in the future that consider a number of factors like population, economic trends. They're essentially capturing the extent to which human beings are going to act to counteract climate change. And there's a high range here, the SSP 8.5, and then there's a lower range. And so one of the things that a utility or operator needs to do is decide what is their risk tolerance and what is their risk level. Climate projections get downscaled to locally relevant scale. So that's kind of 3 to 6 kilometers typically. And so you have a future view of a range of climate variables at a geographic resolution. And then that temporal resolution actually outputs daily values. Depending on what you're doing with this data, you may do it at a decadal level. So that's the level of decades. Just want to be clear, no one can tell you what the weather is going to be at a given point in time on a given day. So this daily resolution is just an artifact of the output of the analysis. So initially, this vulnerability, sorry about that. Initially, you start with a vulnerability analysis similar to kind of that matrix that Morgan teed up, where you're looking at asset groups. So really at a very high level, transmission, substation, and distribution. This is built actually from the bottom up. So we're showing you, what you ultimately produce at a high level to identify where you're going to focus. And so again, exposure, we talked about that, sensitivity and consequence, all previously discussed and redefined here. And here we see down the left side our climate hazards. So heat, flooding, I think you understand. Part of the effort is to determine which hazards are relevant, and the relevant hazards are going to be regional, right? So in very southern areas of the United States, cold and ice isn't, say, in Florida, as much of a concern as perhaps extreme heat. And ultimately, you roll up the uh, assessment of vulnerability at these high levels to allow you to focus your effort. The vulnerability assessment can go down one level of abstraction below and then look at kind of assets within an asset group. So here we're looking at transmission assets, the overhead conductor, underground conductor, the structures, so the poles or towers, and then other components like open air switches and the like. And we're looking at those sensitivities to heat and consequence to heat. So just as an example, so the yellow here, the overhead conductors, showing a medium sensitivity to heat, right? So heat is important, and Morgan kind of teed that up. Consequences relatively high. A given transmission line may serve several substations, and so the loss of the line can be problematic for the system. And so an overall potential rating here would be red, whereas a pole or tower really isn't sensitive to heat. However, its consequence is relatively high, but when you do that multiplication, the potential impact is lower. The vulnerability analysis can also drive down to specific assets. So as an example, on the left here, we see extreme heat in substations, and we're seeing substations. So these are, each dot is an individual substation. This is out of the Duke climate risk and resilience study that my company ICF produced for Duke Energy. And so this is at the individual substation level, and it's showing substations color-coded by the annual number of days with daily temperatures exceeding 110 degrees Fahrenheit in the year 2050. On the right, staying with substations, we're showing flooding. And so it is substations in the 100-year FEMA floodplain, and we have 500-year FEMA floodplain in yellow. So 100 is in red, 500 is in yellow. So vulnerability analysis can get down to the individual asset. So when you do exposure, vulnerability, impact, and consequence, when you tie that all together, that allows you to prioritize assets for adaptation based on kind of overall risk. And so severity we talked about, right, is a kind of likelihood multiplied by hazard. Consequence can include consequence to the system or consequence to customers. Here's just one dimension. You might have customer minutes interrupted or cost. There's a lot going on in this area. Consideration of social vulnerability indices, vulnerable populations. So there are any number of metrics, scores that can be built into consequence to build into this overall risk. And so risk is kind of this overall multiplication and consideration of the aforementioned dimensions. One other thing I wanted to bring up in terms of asset-specific prioritization, imagine substations and heat. You're prioritizing, you've considered exposure. There is also a consideration of the asset itself, and one dimension there could be transformer health. There are health scores for assets, health scores for circuit breakers and things like that. But just thinking about transformers, looking at the 2x2, you have a risk score that would include exposure. It might include consequence that considers the customer profile that station serves, and then transformer health score is one other dimension. So you see here in this upper right quadrant, you have high risk, so that might be high exposure, high consequence by customers served, and then poor health, And so that might help you prioritize. And so this is just a dimension here showing kind of the same data that is up in that left 2x2. Just a couple of other slides. I want to be clear that vulnerability assessment does not just include assets, things, but it includes processes. And so when we do these types of studies, we consider a number of processes that are typically common to utilities, and we'll also consider processes that are specific to the client. But just an example here, load forecasting, the forecasting of load, that's impacted by heat, can be impacted by extreme cold as well, going to be impacted by electrification. But as you see, there are various processes that are common to utilities, and the various climate hazards get considered, and that consideration can be aggregated up to scores, after which the adaptations, essentially, what are you going to do about it, how the process will change, gets rolled into the latter part of the analysis. And finally, just 3 case studies. I know that there'll be more case studies in the latter parts of these sessions. But for flooding, Superstorm Sandy in New York, for Con Edison, significant amounts of damage. Storm surge was greater than ever experienced before, and over 1 million customers out of service. For wind, Hurricane Ida impacted Entergy's transmission system. The transmission lines had been built to withstand kind of 95 to 110 miles an hour, but Hurricane Ida had gusts well in excess of that and took down transmission and resulted in interruptions for weeks. And for heat in 2021 in Spokane, Washington, there was a 1 in 1,000 year heat event with temperatures of around 110 degrees. And the result of high demand and reduced capacity because of high ambient temperatures resulted in some transformer temperatures really kind of above design, and the utility shed about 20,000 customers to protect those transformers and substations. So 3 examples here tying into what we've talked about. And those are my slides. I will come out of sharing and turn it back over to Morgan.